Brilliant. All right, I think we're ready to go. Hello, everyone, and yeah, special good day to all the people who were at the WebRTC Code Lab yesterday. There are going to be quite a lot of like links in these slides, and if you want to follow along, they are online at simple.info/media. You can have a look afterwards. So, I think we've seen sort of two really big shifts very suddenly happening on the web, and I think the first of these is kind of obvious. Kind of the rise of mobile. We've got more mobile phones than pencils or toothbrushes. Someone told me the other day, and all this stuff. But the word mobile kind of hardly covers it. We have all these different devices, and in a sense, the only thing these have in common is that they're all platforms for web apps. But the thing is that it's not just kind of the same old thing on different devices. I think what we're seeing is a complete change in what we're doing on the web and what we can do in browsers. Just some stats about this. This is from a UK Ofcom report recently. Like more than half of us are doing other stuff while we watch TV. We still watch a lot of telly, like 4 hours a day on average in the UK. But we do stuff to do with the telly we're watching, but we also do stuff that's completely unrelated. We watch YouTube videos. We use media on the web while we're watching telly. We love to communicate, and these over-the-top messaging applications like WhatsApp and Snapchat and so on are huge now, much bigger than SMS. Joe McCann, who did this graph, I heard him saying the other day, that this company in Japan, Line, that do over-the-top messaging, in the second quarter of this year, they sold $132 million worth of virtual stickers in their over-the-top messaging service. That's like virtual stickers. It's amazing. But these messaging services are not just about communication. They're also platforms for media and for web apps. So really changing the way we use the web. Now, I guess so. This brings me to kind of I think what's the second big shift in the way we experience the web, what we can do on the web, and that's the rise of media, audio, video, and communication. This figure from Cisco, they're projecting that potentially up to 90% of traffic on the internet will be video within the next few years. This translates to something like 1 million minutes of video crossing the internet every second. This doesn't mean that we're all going to go out and design the next YouTube, but we're coming to expect kind of seamless audio and video and communication in web apps. And we can take advantage of these hugely powerful APIs. And there's this richness of stuff that's now implemented on this huge range of devices. Anyway, first I would like to kind of take it right back. I don't know if anyone remembers this stuff. I'm old enough to remember when this was kind of cool. But now, thankfully, we have the simple beauty of the video element. And one of the nicest things about the video element, it's now supported on this huge proportion of web browsers, which is great. As you can see from the JW Player stats there, we've got great coverage. To show you kind of just how far we've come with the video element, just want to show you something that's been implemented in Chrome. This is the ability to use the internet. Or not. Okay. Let's turn on our Wi-Fi first. This is the ability to use alpha transparency in videos. And what this means is we can do stuff like green screening. Let's see if we've got video there. We've got an internet connection. Okay, have we got anything? Let's see if we can get to Devox. Chug, chug, chug. Let's go forward a bit while that's loading. Now, let's add to this video element a little bit here. And what we have here is the ability to add timing range for the video. So in this example, what we're saying is, can we play this video just from 5 to 10 seconds? Let's have a look at that, in fact, in a demo. We could actually do this. Let's try this on the mobile phone. So I'm using the Chrome DevTools here. I'm going to open up this page on my Nexus here. Let's inspect the tab, and then I'm using the experimental screencasting in the tab there. Let's open it up. And hold on, let's go back there. And let's open that again with it focused and inspect the tab. And if we go to screencasting, you can see there that if I go to play this, it's going to play just a few seconds of the video there. Chug, 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 with terrible internet connection. But you can see that it's just playing those seconds of video. Anyway, let's go back to where we were. Let's see if we can get at the transparency demo now. So what we have here, let's try again. We have no internet at all. Okay. Okay, so here we have two videos playing over a background. These are two videos with transparent backgrounds. And you know what's cool about this is that these, the video elements are just elements. So these are now, transparent, but we can do things like we can drag one over the top of another. You can see there's CSS filters. We can do CSS animations with these. We can even swap out the background with another video and then be playing over another. So, to me, that's fantastic and great for all kinds of green screening apps. So, if you want to play video, you potentially, at this point, of course, going to need different sources for different platforms. Now, we can do that using the source element, and this gives us a really non-hacky way of making it possible to give different sources depending on what we need to use. In this example, we've got just two here, and that in fact covers all the platforms that support the video element now. The video element now on the internet. So if we look at Safari here, you can see just about visible there that that's actually playing the MP4 version, and if we were to open that in Chrome, it would play the WebM version. So just a nice way to do that. And by the way, if you want to get at these properties, you can get at the current source of a video, the actual source that's being used using the current source property of the video element. And video width and video height are the actual, so to speak, frame height and width of the video. The type attribute is optional, but this can give us really good performance on different platforms, because what it means is that the browser can choose which of these formats it supports and not actually have to download stuff just to kind of sniff it to check if it can use it, which means you have less downloads consuming less bandwidth and the ability to actually start playing the video more quickly. So yeah, just a really simple way of better use of the video element there. And don't forget the humble poster attribute. This gives us an image that's played as soon as the video element is displayed. And this is well supported. It can be really good on mobile platforms because you can get. It does mean another download, but it does mean you can get some meaningful content in the element before playback of the video begins. So it's worth considering, I think. Okay, here's the full Monty, and yeah, this shows two things that do not work on mobile. Autoplay doesn't work on mobile for good reason. People don't want video to start playing automatically. For the same reason, you can't script video playback on mobile. Likewise, preload does nothing on mobile. The preload attribute is used to kind of hint to the browser how much buffering you think should take place. that comes to 0 on mobile platforms. If you want to have a look at this, check out Steve Sauder's stuff there. This is great kind of crowdsourced testing, which shows exactly in real life what's happening with the video element there using Preload. Now, so I've shown different ways of setting the source for a video element using the source element. We also now have the ability to do, to set the source using JavaScript to essentially be able to combine chunks of video to create a stream for playback. So a little example here. Let's see again if we can just show this on the phone, because it's nice to see this on mobile. So I'm just going to try and open this on my phone. If I get the URL right. There we go, we've opened that up there. And just wait for that to load, and then inspect that. And again, we're looking at screencasting here. Now what's happening is, this is a bit of a fake. It's actually using XHR to download some WebM video and then using the file APIs. It's just for the purposes of the demo to chunk that up into 5 pieces. And then, but when you can see that we can now play back that video. It's kind of 5 seconds of individual chunks of 5 seconds of individual chunks of video. So yeah, pretty neat there. And a great way of giving JavaScript control over video playback. We can also use this, a really good example, in something called Dash video. Dash stands for Dynamic Adaptive Streaming over HTTP, which kind of does what it says on the tin. This allows us to do things like, adapt to different bit rates depending on the context. The way you do this is to encode your video at different bit rates on the server, and then provide something called a manifest file, which kind of gives a description of the individual chunks of video that you want to use. You can encode an entire video, so have an entire video in different bit rates, or you can have smaller chunks depending on what makes sense. We can actually see this in action here. There's a couple of links there to resources. I don't know if this is going to work over this internet connection, but yeah, you can see that this is getting us video using Dash, actually via a Dash JavaScript library, and then playing it back with different streaming rates potentially. You might have noticed there, in fact, that gave us actually also the ability to work with something called encrypted media extensions. Encrypted media extensions is a JavaScript API that allows HTML media elements, so audio and video, to interact with content protection systems. Now, the reasoning is that like media companies like Netflix, broadcasters like the BBC won't distribute their content unless it's protected. Up until this point, they've used plugins like Silverlight and Flash for this. The aim here is to be able to do that stuff in the browser to avoid those plugins. And there's some links to resources more about EME there. And again, a little example here. There's things that happen like which essentially, I'll turn that off, get rid of the sounds. So what's happening there is that that's actually encrypted video, but when the browser, Chrome, encounters the encrypted video, it fires a need key event, and then the browser can handle that via what are called content decryption modules in order to decrypt and play back that video, and essentially provide a key to decrypt the video. So, yeah, we have something like 85% coverage of browsers that do support the video element. But we live in the real world, and for that we have a bunch of fallbacks. The ability to work with other platforms using HTML only, using video for everybody as an example there, and a stack of JavaScript players that cope with fallbacks as well. You think about fallbacks, you might also want to have a look at can play type. This is a slightly bizarre API, but in that it gives us this wonderfully non-binary results. So it gives you, it's sort of hard to see up there, but it tells us essentially which codecs can be supported by the platform that you're currently running on. So just a way of checking that. And of course, it's not definitely yes or no for anything. Slightly strange that Video WebM on Chrome is given as maybe, but anyway. Now, thinking about fallbacks, thinking about accessibility of video, you know, what do we do about that? How do we do captions and subtitles? Well, we've had for a little while now the ability to use what's called the track element. But let's see that in action now. If we just open that up, chug. Oh my God, it's so slow. What we essentially have while that's loading, I'll just show you the code for that. So we have a video element here, and you can see it has a track element as part of it, and the track element itself points to. Okay.
And the way we access it is changing. The source of that change is you. Developers all.
So yeah, you can see there that the captions are rendering over the video. And then we're actually also listening out for the caption change, what are called queue events, which are firing, and then we're getting that, the text for each queue, and then outputting it in a div below the video. So if we look at the source for that, it's what's called a VTT file in this case. I'll just bump the size up a bit so you can see. And it's a series of these things called queues, which have timing, and then in this case just some text. You can see that actually there's some extra markup on this example because there's ideas that you might want to be able to do layout and so on with subtitles, which is kind of neat. Think karaoke. We've just actually, I've seen implemented in Chrome something called in-band WebVT, which simply bundles the track data inside a video file. So it's all packaged up together. And, you know, the point of this is that you can have one file that can have the tracks built in. So this is very, very cool. Rather than having to distribute, you know, the track file and the video file as a package, you've got that all packaged up in one container. Now, you know, these captions and subtitles are great for accessibility, but they have some kind of nice side effects as well. So, you know, if we've got timed data about what's actually in the video, we can search for that. In this example, I've got the transcripts from YouTube of like hundreds of videos that we've done for Chrome, and then made them searchable just by looking for them. We can then get, we can find those cues, if you can see that. We've got the timed cues there, and then we can click on something, and then it simply sets the source of the video, and at the point where that text occurred. So this is to me, is a way of, you know, making media less opaque, of being able to search and navigate media, and you know, it's pretty straightforward. By the way, if you want to look at YouTube captions, that's the URL. Don't expect you to remember that, but if you have a look at the slides afterwards, that's a way of getting at YouTube caption files. Now, these examples so far have all used cues that have just plain text for subtitles and captions. The thing is, we can also use cues and tracks for any kind of data. You know, we can put JSON in those cues. So in this example, there was a guy, a Googler, who cycled around the campus in Mountain View, and he took video and he got GPS coordinates as he went around. So I put that together as the track for the video, which means that we then have the ability to synchronize movements on the map with movements on the video, and likewise. You know, if you shift the map moves to, you know, to synchronize with that. So I can see a lot of, you know, use cases for this kind of stuff. So we couldn't do any of this without good codecs, you know, especially thinking of the, this kind of multi-platform world, codecs are really, really crucial to preserve bandwidth and get really good quality on, thinking about smaller and kind of more bandwidth constrained devices. Just a quick word of some stuff that we're working on at Google. Of course, there's been a stack of work on VP8, thinking about, particularly about, streaming media and real-time communication. And VP8 is being built into a whole range of devices, including camera chips, which is pretty cool. So you're actually able to encode video in VP8 directly from the camera, which is nice. And work is continuing on VP9. This example here is actually showing VP9 against H.264. We don't have an HEVC like H.265 encoder that would make sense to use in comparison, but the general feeling is that H.265 will be about half the bits of H.264. So you can see that VP9, even as it is now, is looking good in comparison, and I think the quality there is good as well. There's some tools you can use obviously for encoding VP8, VP9 on the desktop, native applications, and of course also cloud encoding services as well for kind of larger scale operations. So great. We have all these ways of playing back audio and video. That's really nice, but of course it would be nice if you could kind of do it yourself on your own device. Well, we can do that, and we have for that an API called Getusermedia. Has anyone here used Getusermedia? Francois. Anyone else used Getusermedia ever? That's amazing. Anyway, so Getusermedia is this API for getting audio and video from your local device. So here's a pretty simple example here. You can see that we're calling Getusermedia. It's on the navigator object. We pass it a constraints object, which you can see up here is just saying nothing but like, get me video. That's all it's saying. Get me the default video. And then in the callback, that's being passed a stream. And then in this example, we're just setting it as the source of a video element. So you can see that in action here. Yeah, I'm calling exactly that code there. And then you can see I'm getting some video from my default camera there. So that's kind of nice. What I love about these APIs, again, is that when they come up against each other, in this example, I don't know if anyone's seen this, but essentially we're getting, so you can see, by the way, that there's a permission bar. You have to give permission to allow use of your camera. So in this example, we're getting video using Getusermedia, and then we're piping that frame grabs from that into a canvas element. Then we're analyzing that pixel by pixel. Then we're analyzing that pixel by pixel and come out with ASCII art instead, which is pretty cute. Yeah, but just the ability to combine these APIs, you get this great richness, I think. So just taking that back, if you remember in this example, the constraints object for this, like describing what kind of media I want to use, was pretty straightforward. We can do more interesting things with that. We can do things like select resolution. So in fact, let me have a look at this on GitHub, if it'll open up. Okay, so in this example, we've got actually 3 different constraints objects, if you can see them there, kind of each representing low, medium, and high resolution. And so then when we click on the button here for low resolution, it's calling Getusermedia with that low resolution there, and then we can go for VGA, kind of, and then bump it up to the kind of full-fat HD, which is pretty nice. Doesn't look very HD to me, but anyway. And this is nice too because, depending on the device, you can choose what kind of resolution would make sense. So, yeah, that's kind of cool. So the other thing kind of obvious that we need to be able to do with when we're getting user media is to be able to choose the source of our mic and camera. We do this again using constraints. Essentially, there's a method to get all the devices that are attached to your machine on the media stream track method, get sources, and that returns the ID of different devices, and then you can use that to actually then choose a camera. So let's do that on the camera. In fact, on the camera. In fact, on the Nexus here. Let's see if we can open a page there. Choke. Wait for it to open. And let's inspect that and see how we go. Again, going to using the kind of experimental screencast API there. So let's have a look. So, okay, I'm in selfie mode at the moment, but then if I change the camera, I can go, into crowd mode. So that's kind of nice. Hello, Francois. And everyone else, hello. So obviously this is particularly important. I'm going to quit out of that. On mobile devices, allowed them, to choose cameras. And there is, by the way, an API spec in planning, which will give like the generic ability to use front-facing or back-facing rather than having to specify a USB ID. We can also do screen capture using constraints with Getusermedia. So a little example here. I'm just going to capture my screen here. Actually, I might have to go to. Let's hang on. Last time I did this, it didn't work, except in. I needed to do this in Canary. So you can see there I'm being asked permission if I want to do that. And this is, it's slightly useless because it's just sharing the screen that's sharing the screen. But you get the idea of this kind of nutty hall of mirrors effect. But, really useful for doing things like, it sounds boring, but, kind of customer support and all that. And loads of use cases there. A lot of people have asked, by the way, about recording video and audio that you get on the web. Where we have something called the Media Stream Recording API for that. This is actually, you can see this for audio in Firefox nightly at the moment. There is an intent to implement in Chrome. If you're interested in this stuff, by the way, there's an API, the Streams API, which has this kind of, it's like a generic API for streams, and it's definitely worth a look. That's in specification at the moment. We also have this API, which is essentially the Taking Photos API. And it gives us the ability, again, thinking about mobile devices, to do things like control zoom and autofocus and so on. So really specifically oriented to, still photos, cameras. So we've talked a lot about video. I just wanted to think about audio on the web. Well, we've got this great API that people may have used called WebAudio. Taking it back, of course, we had the audio element, which again is a beautiful thing, and of course is well suited to just playing back plain old ordinary audio and streams of audio. Now, the problem with the audio element initially, really, what came up was that it didn't work well for gaming apps. And there were reasons for that, that essentially using lots and lots of audio elements is really inefficient and resource hungry. And once we're moving, people naturally, of course, are using mobile devices for gaming. So that really didn't work well at all. So the WebAudio API was developed in response to that to give us this ability to do really high performance with things like multiple sounds, overlapping sounds, and to get very precise timings. And what we get, the model of WebAudio is, if you imagine it as a series of nodes on a graph that can be joined together to do different stuff, so to manipulate audio and also do things like visualization and so on. And you can actually use an audio element as the input for WebAudio. By the way, does anyone remember the BG sound element? My God. There was like this element years ago. The idea was that, when you would load an HTML page, you would get a background sound, which was insane. So no one had control over this, and it was hideous and it soon dropped. But anyway, That was where the audio element originally came from. Web audio does a lot of different stuff, which is fantastic, and I'm not going to go into it now, but you can do a huge amount of, number of audio tasks really very easily with web audio. And it's really well supported now. We most recently have Getusermedia support as input on Chrome for Android, which is fantastic. As I'll show, we can use web audio as input to WebRTC, so to communicate to someone else with processing along the way. If you want to find out more, I'd recommend anything by Chris Wilson. He's one of the guys who's on our team who's worked on the web audio spec, and everything he's done is great demos as well. So yeah, like I say, we have the ability to use Getusermedia, so mic input, as the source of audio for web audio. Pretty straightforward to do that here, just to create a node from the stream returned by Getusermedia. We can see that in Getusermedia. We can see that in action here, this vocoder demo. This is probably going to make hideous sounds, but anyway. Yeah, sorry about that. But you can see here that blah, 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 blah. I'm being recorded by the microphone, and then some effects are going on, and then that's being piped via web audio into to create the visualizations there. So nice stuff. Again, these APIs coming up against each other. And like I say, we can pipe mic input into processing from web audio, and then pipe that into RTC peer connection, which I'll talk about in a while, in order to then give that to someone else. There's a demo there if you want to have a look. So to be able to communicate processed audio, which is fantastic. Chris Wilson's also worked on this new spec, the Web MIDI spec, which is now available. It gives us the ability to work with MIDI devices, things like keyboards and so on, to have really proper music support, instrument support on the web. And that's now available in Chrome on the Mac. There's a kind of huge range of demos that I could do here. I just might have a look at a couple of these. So yeah, this is. We better get the audio for this, sadly. But can people hear that at all? But again, this is all done using web audio, which is neat. And yeah, just the ability essentially to create instruments as well as to process audio, I think is pretty nice. Same with Chris Wilson's crazy synth here. So, it's a synth, and it's built with web audio, and it's working in a browser. I think that's. But when you hook that up to MIDI devices, you get some really interesting possibilities. So this is all great. We've got audio and video and processing of audio and video. But of course, what would be really nice is that we could communicate this stuff to someone else. And for this, we have WebRTC. This is a project to enable real-time communication in the browser. And it came out of this need to do real-time communication on the open web in a way that was open source, that didn't need plugins, that was free for the end user and for the developer as well. And maybe the most, sort of radical thing about WebRTC is that it's inherently peer-to-peer. So the architecture of WebRTC is designed, in the old days we had these kind of real-time communication systems which were inherently kind of centralized. You were using someone else's service, going via a highly simplified diagram, but via someone else's servers. And what WebRTC gives us is the ability to, again, this very, very simplified diagram, to go directly peer-to-peer for communication, inherently much more efficient. As I'll explain, nothing is that simple in a world where we have NATs and firewalls, and we need to coordinate messaging. But we have really good support for WebRTC now, lots of platforms, Chrome and Firefox. Opera, I don't know if people have seen, but Opera 18 now supports the WebRTC APIs, and they're they're committed to support on mobile as well, which is really cool. Internet Explorer and Safari, I don't know. People may have seen Microsoft released a kind of alternative spec for WebRTC. We haven't heard much from them for a while. You know, we've also had, I don't know if people have used Qt framework, but they've moved to Chromium recently, which gives us access to a stack of APIs, including the WebRTC APIs, on a huge range of, you know, native and embedded platforms. So, you know, I think that's really exciting too. So it gives us now, you know, we've got well over 1 billion WebRTC endpoints, a lot more predicted for the near future. The kind of obvious use case for this stuff is, of course, video chat, but we've seen some really interesting other stuff coming up. Just recently, near where I live in South London, Sky did this live TV interview using WebRTC. And, you know, the old days, you needed all this stuff. You know, you needed these things called OB trucks and all these personnel, and, you know, it was expensive and difficult and, you know, all that stuff. What they used was this, which is like, you know, one of these cameras like I've got in my bag, and I guess a sort of €100 Yeti mic. So, you know, this is really cool. I like this. You know, this kind of puts, I feel like it puts this kind of stuff in the hands of everyone. You don't need all that stuff that you used to do this kind of broadcasting. So what do we need for this? Well, there are kind of different tasks that we need to do in order to do real-time communication. You know, we need to be able to get audio and video. We need to be able to establish a network connection between peers. And then once we've got the network connection, we need to do really, you know, really high quality and reliable streaming of audio and video. And there's a lot in that, you can imagine. The other thing about WebRTC is it's always been committed to the idea that you could do real-time communication of arbitrary data, so not just audio and video, but any kind of binary data or textual data. And that's kind of interesting. I think that's, you know, potentially where some of the more interesting stuff is actually coming from at the moment. So for this, we have 3 JavaScript APIs, main APIs essentially. I've talked about Getusermedia. RTC peer connection is the API for making the network connection, and then for actually doing audio and video streaming, and doing the whole lot in a way that's completely secure, so encryption all the way. Rtc Data Channel is like a kind of child of RTC peer connection, and this is the API that allows streaming of arbitrary data. So, yeah, RTC peer connection, you know, the concept is really simple. You get a media stream and then you pipe it into the RTC peer connection, and the other end you have another media stream that you can do something with, like plug it into a video element. Of course, things aren't that simple because we need to cope with NATs and firewalls. You know, we have to do 2 things to cope with that. So we have to be able to cope with the real-world networks, and we also need to be able to signal between the endpoints of a WebRTC call using something called signaling, and that's not defined by the WebRTC spec. So essentially exchanging metadata done by a signaling process, which, you know, you can use anything you want, but this is not specified by WebRTC. And there's a stack of stuff that RTC peer connection is doing, you know, under the hood, so to speak. It's working out the best way to connect between points, essentially using something called the ICE framework to get through NATs and firewalls. It's then doing a stack of audio and video jobs like echo cancellation, avoiding video jittering, and so on, you know, and so on and so on. If you want to have a look at this stuff, a really simple example there, I needn't look at that now. The kind of full-fat, I don't know, video chat demo that Google maintains is at apprtc.appspot.com. This is a great place to get started because it has really verbose logging, and it's kind of the full, you know, the full Monty of video chat applications. Rtc Data Channel, like I say, is the API for arbitrary data. You know, imagine you've got the, I don't know, players in a game who want to exchange positions. So you can do that, you know, in a way that it's very like the WebSocket API, but the whole point is that you're exchanging data directly between peers. You're not going via a third-party service, which makes it lower latency, more efficient. And we now have the ability to use reliable or unreliable transport. What this means is, say, for a game, you might want higher performance. You don't care if some packets get lost. For something like file transfer, we've got to make sure every packet arrives, even if that results in lower performance. Again, a little demo there if you want to have a look. Kind of nice app we've seen with this is ShareFest. This allows file sharing using Rtc Data Channel. So, yeah, if I just select a, let me think, hang on, random file here. This is like a picture of our local pub in London. Now, what I'm doing here is I'm making getting a URL there from ShareFest, and when I open a new browser window with that URL it gives me, it's setting up Rtc peer connection, and then exchanging that image peer-to-peer. And then you see at the other end, I've opened that up directly from that browser tab. So, a kind of simple way of doing file sharing without using an intermediary server. Another, I think, more ambitious project, you should have a look at this, is something called Peer CDN. What you do is essentially you include their JavaScript library, and then Peer CDN, the JavaScript, will attempt to download whatever it is, whatever the assets are on your page using Rtc Data Channel from other peers, rather than actually downloading stuff from your server. So, I mean, we'll see where this goes, but essentially this is a kind of, peer-to-peer with peer-to-peer file distribution with WebRTC, so kind of nice. Just a couple of tips for using WebRTC if you're working on multiple devices here. These are from a great video, a presentation from some guys from V-Line. And the biggest thing here is, you've got to think about resolution if you're working with video on mobile, of course. Another thing that, I don't know if people noticed, but thinking about desktop, the permissions interface, like the allow button, is really easy to miss. People who've never seen this before will miss that stuff. So if you're building WebRTC apps, make sure to make that obvious. Put something in the interface that makes that show up better. There's a stack more information about WebRTC on the web. One other thing you may want to look at is Chrome WebRTC internals. This is like a Chrome information page that will give you stats and visualizations of WebRTC calls that are in progress. Really great for tweaking performance between devices. The book is pretty good too. You can get that for your Kindle. I thought we could just try a little demo. I can't believe this will work here, but anyway. If anyone's got a laptop open, if they want to go to, it's like talkie.io/devox. This will be a miracle if we'll get any connectivity at all. But if you go to that page, we might just be able to hook up with someone if there's anyone out there. So it's just to show you the URL again. It's talkie.io/devox. Here we go. We got someone. We've got two someones. Hello. But this is a nice app. This is kind of essentially just doing a really simple connecting everyone to everyone approach. But you can see even in this kind of constrained Wi-Fi, that's working pretty well. Hello. Brilliant. That's really nice. I'm amazed it's working at all, especially with like 3 or 4 streams. That's cool. Another stream too. That's really nice. It's a nice way, if you want to have a meeting with someone via video chat, you can just share a URL. This is what I like about WebRTC. Okay, so, 2 places to look for all this stuff to see what's working where. ChromeStatus.com, these kind of 2 old friends that have recently been updated. 2 good ways to find out what's working on what platforms, ChromeStatus.com and caniuse.com. And that'll give you information about all the APIs I've referred to. Thank you very much. I'll be around for a little while today. Like I say, these slides are at simple.info/media, but Yeah, I'm happy to take any questions about the media APIs. Any feedback people have actually used these APIs. Yes.
In the WebRTC, is there a zip stack running under it?
So do you mean in terms of signaling?
Yeah.
Yeah, so signaling is not defined by the spec, and it's not essentially implemented by, by RTC peer connection. So you can use any protocol you like for signaling, any mechanism as well. I mean, the CodeLab example I've given there uses socket.io on Node, which works pretty well for a small number of users. But then you can move to, say, using an XMPP server or whatever you like for really high traffic examples. There have been moves. The actual format of the data that WebRTC apps exchange is in SDP, and then there are some moves to think about whether it might be better in JSON format and so on. But there are also gateways to work with WebRTC apps with the outside the world of SIP and so on. And because WebRTC was designed kind of standards in mind to deal with existing communication systems, so VoIP, video conferencing, and the world of PSTN, so plain old telephones. Yeah, so it's out there, and there are JavaScript SIP libraries as well. Yeah. Anyone else? God, it's really hard to see under these lights. Okay, if no other questions, we'll leave it there. Thank you very much. And yeah, have fun with these APIs. They're fantastic. I think especially WebRTC is like a great feat of engineering. Thank you.